Welcome to the deep dive.
So today we're looking at something pretty amazing, actually. Something you see all the time, but maybe don't think too much about. The soap bubble.
Oh, absolutely. They're fascinating,
Hmm.
fleeting, but packed with physics.
Right. For most of us, it's just, a childhood memory, that shimmer of color before it pops.
Yeah.
But for scientists, it's way more. It's like a perfect little sphere showing off all these forces.
Exactly. And, for this deep dive, we're really digging into some classic work by C.V. Boyce, a foundational text on this.
Right. The famous book. I remember seeing references to it.
Yeah. His whole mission really was to say, look, this isn't just a toy.
Mm.
It's a perfect little physics laboratory floating right there in front of you.
Yeah.
He wanted to spark real curiosity about fundamental science using these simple-looking demonstrations.
Simple but revealing complex stuff like geometry, chemistry.
Everything from how planets form to, the math of surfaces, it's all in there. Okay, let's start at the beginning then. That perfect sphere floating. What's the absolute core force holding it all together, preventing it from just poof, disappearing?
Well, the main force we're talking about is its surface tension.
Surface tension.
Boyce put it really nicely. He said the liquid acts like it has an elastic skin.
An elastic skin, like a balloon.
Sort of, but it's intrinsic to the liquid itself. Imagine this thin, invisible layer stretched over the surface, and it's constantly trying to pull inwards to shrink. It wants to achieve the absolute smallest surface area possible for the volume it contains.
Oh, okay. And the smallest area for a given volume is?
A sphere. Always a sphere. That's why water forms drops, and why a soap film traps air and snaps into that perfect round shape.
It makes sense, but okay, if water has this skin naturally, why do we need soap? You can't really blow a bubble with just water, can you? It just breaks.
That's a really crucial point. Pure water actually has a very high surface tension. Really strong skin, you could say. About $3 soar grains per inch.
Stronger than soapy water.
Yeah, significantly. But the problem is that pure water film is incredibly fragile. It evaporates super quickly. It drains almost instantly. It just can't hold together.
So the soap, what does it do? Weaken it.
It does weaken the tension a bit, down to maybe $2 Fact2 grains per inch. But more importantly, the soap molecules arrange themselves into this kind of double layer, like a microscopic sandwich.
Okay.
And this layer does two things. It reinforces the film, gives it more viscosity and elasticity, and crucially, it dramatically slows down the draining and the evaporation.
So it makes it durable. It buys us time to actually see the bubble.
Exactly. It gives the film the stability pure water just doesn't have.
And getting that stability right was key for these classic experiments, I imagine. Boyce was quite specific about the recipe, wasn't he, for the bubble solution?
Oh, absolutely meticulous. If you wanted the kind of long-lasting, beautiful films he described, you couldn't just use any old soap.
No tap water and dish soap, then.
Definitely not back then. He recommended pure oleate of soda, basically, a really high-quality soap mixed with glycerin.
Glycerin. I've heard that helps bubbles last.
It's the secret weapon, really. Glycerin is thick, viscous, and it's hygroscopic.
Meaning it attracts water.
Exactly. It holds onto water molecules, fighting evaporation, keeping the film moist and strong for much longer.
And the water itself.
Had to be pure, distilled or deionized. Tap water is full of minerals, tiny impurities.
Which would mess with the surface tension.
Instantly. Even tiny amounts can disrupt that delicate balance needed for a stable film. Remember, he didn't have modern detergents like, Tide or whatever. Purity was everything for consistency.
Okay, so we've got this idea of an elastic skin. It sounds intuitive, but how do we, prove it's a real physical force, something you can actually measure? What's the simplest way to see it in action?
Probably the easiest demonstration uses something really common. A painter's brush, like a camel hair brush.
Okay.
When the brush is dry, the hairs are all separate, right? They stick out.
Yeah, they're fluffy.
But then you dip it in water, and when you pull it out, what happens?
They all clump together into a point.
Exactly. Now, why? We just say, oh, it's wet.
But it's more than that.
It's way more than that. It's not just passive wetness. It's the water's surface skin actively contracting. That thin film connecting the hairs is pulling inwards, trying to minimize its area, and that pull is strong enough to physically drag all those hairs together.
So the skin is literally pulling the hairs into that shape.
It's a direct, visible effect of that contracting force. Undeniable.
Okay, I like that. And this idea of the liquid resisting being stretched. There was an analogy in the source material about an India rubber drop.
Yeah, that's a good way to visualize the elasticity.
Yeah.
Think about a big, heavy drop of water hanging from a tube.
Okay, like from a leaky faucet.
Right. It stretches downwards under its own weight, forming that neck.
Yeah.
It resists for a moment and then snap, the neck breaks and the drop falls.
Mm-hmm.
Now compare that to, say, putting a heavy liquid inside a small bag made of India rubber.
Okay, the bag stretches.
It stretches, it resists the weight, but eventually, if it's heavy enough, the rubber tears and the liquid falls out.
So the water drop behaves like the rubber bag, resisting the stretch.
In principle, yes. It shows water has that elastic quality, it resists being deformed, but there's a key difference.
What's that?
Rubber isn't perfectly elastic. If you stretch it too much, it might stay stretched, or it weakens.
Right.
Liquid film, though, theoretically, it's perfectly elastic. It can stretch, it can compress, and as long as it doesn't break, it wants to snap back to its minimum energy state. There's no internal friction causing it to lose energy like rubber does.
The perfect elastic membrane. Wow. And this perfect skin, even on pure water, has actual strength, like measurable strength.
Surprisingly strong, yes, even though it feels like nothing. Think about the floating frame experiment boys described.
A wireframe floating on water.
Exactly. A clean wireframe carefully placed on the surface of pure, clean water. The surface tension, that elastic skin alone, holds the frame up. It literally floats on the skin. And he measured it. He found you needed about 1/4 of an ounce of weight placed on that floating wire frame to finally break the tension and make it sink.
1/4 of an ounce doesn't sound like much, but for just water.
It's significant. It shows that invisible skin is exerting a real, measurable upward force. It's the same reason you can carefully float a needle on water, or why insects can walk on it, or why if you wax a fine sieve properly so water doesn't wet it.
You mean coat it in paraffin?
Right? Coat it thoroughly. Then that sieve, even with thousands of holes, can actually hold water. The surface tension across each tiny hole acts like a continuous sheet, holding the water back.
That's amazing. It acts like a solid surface almost.
In that specific context, yes.
And this leads us straight into capillarity, doesn't it? When the skin pulls water up against gravity.
Exactly. Capillarity from the Latin word for hair, capillus, because it's most obvious in hair-thin tubes.
Yeah.
If you stick a very narrow glass tube into water, what do you see?
The water level inside the tube goes up, higher than the water outside.
Right. And why? Because the water's elastic skin adheres, it sticks, to the glass wall inside the tube. This creates that curved surface, the meniscus.
The upward curve we see.
Yes. And the tension in that curved skin is pulling upwards, strong enough to lift the entire column of water below it against gravity.
Wow. And you said the narrower the tube.
The higher the water climbs. Because you have more edge, more skin pulling relative to the small amount of water weight inside. If the tube was truly as fine as a human hair, the water would rise quite high.
So that's how plants get water up their stems. Through tiny tubes.
That's a huge part of it, yes. Capillary action in the xylem. It's surface tension doing the work in those microscopic channels, lifting water meters high.
Nature is brilliant. And it uses the skin for other things too, like water spiders walking on water.
The water spider, or water strider, is the classic example. It looks impossible.
It really does.
Their feet have special non-wetting hairs, and they literally just dimple the surface. They push down slightly.
Creating little dentists?
Exactly. And the surface skin, trying to stay flat, pushes back up around those dents, supporting the spider's weight. It's like they're walking on a trampoline. Lord Rayleigh even photographed the shadows of those dimples to calculate the force.
He calculated the force from the shadows. That's incredible.
Proving it was a real, measurable upward pressure.
And you mentioned earlier a connection to mosquitoes. How does surface tension relate to them?
Ah, yes. Mosquito larvae and gnat larvae, too. They need to breathe air, but they live underwater.
Right.
So they hang upside down just beneath the surface film. They have a little breathing tube, a siphon, that pokes through the elastic skin. And the tension of that skin is actually strong enough to hold them there, suspended, while they breathe.
Wow. So they're literally hanging from the water skin.
Pretty much, yes. Which gives us a way to control them.
Wow.
If you spread a very thin layer of oil on the water surface, oil is an impurity. It drastically reduces or even destroys the surface tension.
So the skin collapses?
Effectively, yes. The larvae lose their anchor point. They can't hold themselves up to breathe through the siphon anymore, and, well, they drown.
A direct application of physics to pest control. Amazing.
Yeah. And it's been known for a very long time.
It seems like tiny changes on the surface have big effects. What about that weird duckweed experiment? You said if you have duckweed floating and you wet one piece.
Ah, yes, that's a lovely one. It looks like magic or magnetism.
It does. A wet piece attracts other wet pieces,
Yeah.
but repels dry ones.
How? It's all about the shape of the water right around the meniscus. When a piece is properly wetted, the water climbs up its sides slightly.
Creating a tiny hill of water.
Exactly, a region of higher curvature. Now, surface tension always wants to flatten things out, minimize the total area, so another piece that's also wet, also creating a little hill.
They get pulled together to flatten the hill.
Precisely. The tension pulls them towards each other to reduce that overall curvature. But a dry piece of duckweed, water actually curds down away from it. It creates a little depression, a valley.
Ah, so hill repels valley.
Effectively, yes. The differing curvatures create tiny pressure differences in the surface film, and the dry piece gets pushed away from the wet piece. It's all driven by the geometry of the water skin.
It's like a miniature gravitational field on the surface.
That's a good way to think about it, yeah. The landscape of tension.
So if the shape dictates movement, can we change the landscape using chemicals, like that tug-of-war demonstration?
Absolutely. This shows that different liquids have different skin strengths. Water, as we said, has quite a strong tension. Alcohol, much weaker.
Right.
So if you take a shallow white dish with a thin layer of water and just touch a drop of alcohol to one side,
What happens?
instantly, the stronger water skin surrounding the alcohol drop pulls away violently. It yanks the weaker alcohol film backwards, almost like ripping a hole in it. You see the water rush into that space, leaving a clear patch where the stronger water skin won.
A visual tug-of-war. That's dramatic.
Very. It happens in a flash.
And this idea of stronger tension winning. That's key to understanding how even microscopic amounts of stuff like oil or grease can affect a huge water surface, right?
It's incredible how sensitive it is. Lord Rayleigh did amazing work on this. He wanted to know how little oil it took to stop camphor from dancing on water.
Camphor. Little bits of camphor normally zip around on clean water, don't they?
Yeah, they dissolve unevenly, changing the tension locally, which propels them. But Rayleigh found that an oil film just 1/2 millionth of an inch thick was enough to completely stop the camphor's movement over a large area.
1/2 millionth of an inch. What is that even?
It's almost unimaginably thin. Way, way thinner than a wavelength of light. Maybe 1,000 times thinner than a human hair. A practically invisible molecular layer.
And that can kill the surface tension effects across a whole basin of water.
Completely. It just shows how potent these surface effects are.
And we use this potency for cleaning too, like getting out a grease spot.
Exactly the same principle.
Mm.
Grease itself has very low surface tension. It's a weak spot on the fabric, let's say.
Okay.
If you apply something like benzene, which has a much stronger surface tension around the edge of the grease spot,
The stronger benzene skin pulls on the weak grease skin.
pulls hard. It drags the greasy molecules inwards, away from the clean benzene area, concentrating the grease into the middle of the spot. Makes it easier to lift out. It's like corralling the grease.
Chemical corralling. I like it. And this brings us to that old phrase, oil on troubled waters. Did that actually work? Could sailors calm waves with oil?
Yes, it genuinely worked, and sailors knew it for centuries before science fully explained it.
Really?
Oh, yeah. If you were in a small boat in choppy seas, pouring just a little bit of oil, maybe olive oil overboard could noticeably smooth the water surface around the boat.
How large an area?
Maybe 20, 30 yards across, depending on the conditions. The oil spreads out incredibly fast into that ultra-thin film we talked about.
So maybe only 120,000th of an inch thick?
Something like that, yeah. And this thin film drastically lowers the surface tension of the water beneath it.
And lower tension means?
It means the water surface finds it much harder to form those small, sharp, choppy ripples caused by the wind. It doesn't stop the big ocean swells, the large waves.
No, you wouldn't expect it to.
But it smooths out the surface texture, dampens the small-scale roughness, makes it feel calmer locally. It's a very real effect.
Okay, we've seen the skin exists, it's strong, it's sensitive. Now let's think about shapes. You said surface tension always pushes for a sphere, minimum area, but here on Earth, big drops aren't perfect spheres, are they?
No, they're not. Gravity spoils the perfection.
How so?
Well, the sphere is the ideal minimum area shape. That's what surface tension wants. But if a drop gets large enough, its own weight starts to matter.
Like a big raindrop or a bead of mercury on a table.
Exactly. The downward pull of gravity overcomes the inward pull of the surface tension, squashing the drop, flattening the bottom. It becomes sort of bun-shaped.
So only really tiny drops look perfectly round.
Pretty much. Microscopic water droplets, or small drops dusted with something like lycopodium powder, which stops them spreading. For those, the surface tension force is dominant compared to their tiny weight, so they stay almost perfectly spherical.
Right. So if we really want to see what shape surface tension creates all by itself, without gravity messing things up, we need to cheat gravity.
We need to neutralize it. And that brings us to one of the most famous experiments in fluid physics, Plateau's experiment.
Joseph Plateau, what did he do?
He had this brilliant idea. He wanted to make a large blob of liquid effectively weightless so only its own surface tension would determine its shape.
How on earth do you make something weightless?
Not truly weightless, but neutrally buoyant. He used oil, which is denser than alcohol but less dense than water.
Okay.
So he made a mixture of alcohol and water, and he painstakingly adjusted the proportions until the density of the alcohol-water mix was exactly the same as the density of the oil.
So if you put the oil in that mixture.
The upward buoyant force from the mixture perfectly cancels out the downward force of gravity on the oil. It just hangs there, suspended, free from the distorting effect of its own weight.
And what happened to the oil?
The moment he achieved that neutral buoyancy, the large blob of oil immediately pulled itself into a perfect, stunning macroscopic sphere, floating right there in the middle of the tank.
Wow. Just pure surface tension at work.
Exactly. Gravity was taken out of the equation, and the oil instantly adopted the minimum surface area shape dictated solely by its own cohesive forces.
And Plateau doesn't stop there, did he? He used this sphere to model planets.
That was the really mind-blowing part. Once he had this perfect weightless liquid sphere, he could study its dynamics. He introduced a small spindle, like an axis, through the center of the oil sphere.
And spun it.
Yeah. And as the sphere rotated faster, what happened? It started to flatten at the poles and bulge out at the equator.
It became an oblate spheroid.
Precisely. Just like the shape of the Earth or Jupiter or any rotating celestial body that was once molten or gaseous.
So he showed that shape could arise just from rotation and the liquid's own internal forces.
Yes. It was a direct visual demonstration of the physics shaping planets done in a simple glass tank. A connection from the microscopic forces in a liquid drop to the scale of the cosmos.
Incredible. Okay, let's shift from a blob of oil to a soap film, like in a bubble.
Yeah.
You mentioned earlier it has two surfaces, inside and outside.
That's right, a crucial difference. A drop has one surface. A film is a thin layer of liquid with air, or another gas, on both sides, so you have an outer skin and an inner skin.
And both are pulling, so the total tension is doubled.
Effectively, yes. Even though the soap solution itself has a weaker tension than pure water, around $2 grains per inch per surface, the fact that you have two surfaces working together makes the film quite strong.
Strong enough to demonstrate easily?
Oh, yeah. The classic way is with a wire ring and a piece of thread.
Okay, how does that work?
You dip a wire ring, maybe a few inches across, into soap solution to get a flat film across it.
Like a little window pane made of soap film.
Exactly. Then you carefully lay a small loop of fine cotton thread onto the surface of that flat film. Initially, the thread just lies there, maybe a bit loose.
Okay.
But then you take a needle or something sharp and you carefully pop the film inside the loop of thread.
So the film inside the loop vanishes.
Right. And the instant it does, the remaining film outside the loop with its doubled surface tension contracts powerfully. And what does it do to the thread?
It pulls it outwards.
Pulls it perfectly taut, instantly snapping the thread loop into a precise geometric circle.
A perfect circle. Why a circle?
Because the remaining film is trying to minimize its own area outside the loop, and the shape that encloses the maximum vanished area inside the loop for a given perimeter, the thread length, is a circle. The film's tension forces the thread into that optimal shape. It's a beautiful demonstration of the force acting uniformly in all directions.
Wow. Okay, now for the really tricky part, the thing that seems backwards, pressure inside bubbles.
Yes, the pressure paradox. This always surprises people.
Lay it on us. What's the rule?
The rule is, the smaller the bubble, the greater the pressure inside it.
Smaller bubble, higher pressure. That feels wrong. Surely a big bubble has more air squeezed in.
Intuition leads us astray here. Think about the curvature. A small bubble has a much tighter, sharper curve to its surface than a large bubble.
Okay, yeah, it's more sharply bent.
To maintain that sharp bend against the constant inward pull of the surface tension, which wants to flatten it, the air pressure inside has to push outwards harder. A larger bubble has a gentler curve, So the internal pressure needed to balance the surface tension is lower.
So higher curvature requires higher pressure to fight the tension.
Exactly. The pressure is inversely proportional to the radius.
And the classic proof involves connecting two bubbles.
The definitive proof. You blow one small bubble and one large bubble, maybe on the ends of a T-shaped tube with a valve in the middle.
Got it.
Keep the valve closed initially. Then, you open the valve, connecting the insides of the two bubbles. What do you think happens?
Well, based on what you just said, the high-pressure small bubble should push air into the low-pressure large bubble.
Precisely. The smaller bubble immediately starts to shrink, deflating as its air flows into the larger bubble, which begins to grow even bigger.
The small one inflates the big one.
Always. It continues until the small bubble completely disappears, merging into the large one, or until the large one gets so big it bursts.
That is counterintuitive, but makes sense with the curvature argument. It explains why phones are unstable too, doesn't it? Little bubbles feeding the bigger ones.
Absolutely. Foam is a dynamic system constantly trying to reduce its total surface energy. The small bubbles have higher internal energy due to pressure and are inherently less stable, so they disappear over time, transferring their air to the larger, lower pressure bubbles. It's like thermodynamic survival of the fittest for bubbles.
Okay, so spheres are the default. What about other shapes, like cylinders, if you make a soap film cylinder between two rings?
Cylinders are interesting and much less stable. Mathematically, the curvature of a cylinder wall is only in one direction around the circumference. Along its length, it's flat.
Got it.
This means, for a given diameter, a cylinder has only half the inward curving force, and thus needs only half the internal pressure compared to a sphere of the same diameter.
Half the pressure.
Yeah.
Does that make it unstable if you, say, blow into it?
Highly unstable. If you increase the volume slightly by blowing in, the cylinder radius gets bigger. This reduces the curvature, which lowers the pressure needed to maintain it. So the pressure inside becomes even higher relative to what's needed, causing it to expand even more. It's a runaway effect.
It wants to bulge out and break.
Exactly. And there's a critical length limit, too. C.V. Boyce calculated it. A soap film cylinder can only be stable if its length is less than its circumference.
Less than pi times the diameter. Roughly $3 for 7 print.
Precisely. If you try to make it longer than that, the surface tension will inevitably cause it to neck down in the middle and break apart into a series of smaller spherical droplets. Minimum area wins again.
Fascinatingly specific math. But the most elegant non-spherical shape has to be the one between two parallel rings. The catenoid.
Catenoid. Mathematically beautiful. It's the shape a hanging chain makes, a catenary curve rotated around an axis.
So when you dip two rings in soap and pull them apart, you get that wasp-waisted shape.
Yes, that beautiful inward curve at the middle, flaring out towards the rings. What's amazing about the catenoid is that it's a minimal surface.
Meaning it has the smallest possible area for the boundary conditions, the rings.
Yes, but it also has another property. Its mean curvature is 0. The inward curve at the waist is perfectly balanced by the outward saddle-shaped curve as you move towards the rings.
And 0 mean curvature means what for the pressure?
It means the pressure inside the catenoid film is exactly equal to the atmospheric pressure outside. Unlike a sphere or a cylinder, there's no excess internal pressure needed to maintain its shape. It's perfectly balanced.
State of pure tension equilibrium. Beautiful.
It is. But even this perfection has its limits.
You can't pull the rings too far apart.
No. There's a critical separation distance. Boyce gives it as about $3 fretho times the diameter of the rings. If you pull them even a tiny bit further apart than that,
it snaps.
Instantly, the minimal surface configuration becomes unstable, and the film breaks violently, collapsing back to flat films on each of the two rings. It shows there's a precise mathematical boundary even for these equilibrium shapes.
We've seen the static geometry. Let's look at liquids in motion. Lord Rayleigh again, right? Studying jets of water, like from a tap. They look like solid streams, but they're not.
Not for long, no. That instability we saw in the static cylinder film applies directly to a moving jet of water.
The surface tension wants to break it up.
Always. The elastic skin is constantly pulling on that cylinder of water, trying to achieve the minimum surface area shape, which isn't a long cylinder, it's
a series of spheres. Drops.
Exactly. So the smooth stream quickly develops bulges and necks due to tiny vibrations or imperfections, and the surface tension pinches off those necks, breaking the stream into a sequence of droplets. Rayleigh showed this happens at a very predictable rate, governed by the fluid properties and the jet diameter.
So the steady stream is actually a rapid-fire production line of drops.
Pretty much, yes. But Rayleigh found something even more amazing. He could control that breakup
How?
by introducing a specific vibration. If he vibrated the nozzle where the water came out, using something like a tuning fork.
So imposing a regular frequency onto the jet.
Yes. The jet would then break up in perfect synchrony with that vibration. Instead of a slightly chaotic stream of different sized drops, you'd get a beautiful, perfectly regular procession of identical drops, all exactly the same size and spaced evenly apart.
Wow. He could make it orderly just by vibrating it.
He could. The imposed vibration essentially dictated the points where the constrictions would form and break.
And this isn't just a curiosity, is it? This principle is used today.
Oh, absolutely fundamental. Think about inkjet printers.
They need to produce tiny, uniform drops of ink very precisely.
Exactly. They use piezoelectric elements or heaters to create precisely controlled pressure pulses or vibrations, firing out perfectly uniform droplets of ink at incredibly high frequencies, based directly on Rayleigh's discovery about vibrating jets.
Amazing. From 19th century physics to my desk jet printer.
The lineage is direct.
Now, before we leave jets, you mentioned something truly bizarre earlier, a water telephone. How could a stream of water possibly carry sound?
It sounds completely nuts, doesn't it? But it was a real invention developed by Chichester Bell and Graham Bell. Yes, that Graham Bell family.
Seriously, how did it work?
They exploited the extreme sensitivity of a water jet's surface tension to vibration. You needed a strong, steady jet of water forced through a very fine nozzle.
Okay, a high-pressure, thin stream.
Right. Then you'd place something that could vibrate, like a thin piece of wood or rubber, maybe connected to a diaphragm, like in a microphone, so it just touched the stream near the nozzle.
So sound waves hitting the diaphragm would make the wood vibrate against the water jet.
Exactly. And those tiny vibrations imparted to the base of the jet were enough to modulate the stream's breakup pattern down the line.
Modulate how?
It changed the pattern or timing of the droplet formation slightly in sympathy with the vibrations, and somehow this produced sound.
Yes. If you let the jet strike another diaphragm further down, connected to an earpiece, the impact of the modulated stream could reproduce the original sound. The jet acted like an amplifier and transmitter. You could apparently hear loud ticking, or even musical notes quite clearly. A water-based telephone. That's astonishing. It shows just how sensitive that fluid column is.
Incredibly sensitive to tiny disturbances.
So we've hit it with mechanical vibrations, sound vibrations. What about electricity? What does static electricity do to water drops?
Electricity has a dramatic effect. If you take something like a stick of sealing wax, rub it to give it a static charge,
Okay, build up some static.
and then hold it near a stream of water drops falling from a nozzle.
What happens? They're attracted.
No, the opposite. Because the drops are conductive, they pick up the same charge as the sealing wax through induction as they form, and like charges repel.
So the falling drops push each other apart.
Violently. Instead of a neat stream, the drops scatter outwards in all directions, like water shrapnel. The electrical repulsion completely overcomes gravity and cohesion.
Total chaos just from a nearby static charge. Okay, what if you charge the nozzle itself or the water supply instead of just holding something nearby?
That produces the opposite, and maybe even more interesting effect.
How so?
If the jet itself is electrically charged as it emerges, the charge residing on the surface actually stabilizes the stream.
Stabilizes.
The mutual repulsion of the charges along the surface acts as an outward pressure, counteracting the inward pull of the surface tension that normally wants to break the jet into drops.
So the electricity fights the surface tension.
Effectively, yes. The result is the jet holds together as a continuous, smooth cylinder for much, much longer before eventually breaking up further down. It looks like a coherent, glassy rod instead of a stream of drops.
Wow. And this extreme sensitivity.
Huh.
The source mentioned it could be used for early wireless communication.
Believe it or not, yes. The stability of that charged jet is so sensitive to external electrical fields.
That even a weak radio wave or a spark from across the room could affect it.
Exactly. Scientists found that a faint electrical disturbance, like the spark from a simple telegraph transmitter some distance away, could be enough to momentarily disrupt the charged jet's smooth flow, causing it to visibly scatter or break up.
So the water jet acted like an antenna and a visual indicator.
A very primitive but functional receiver for wireless messages, yes. It turned an invisible electrical signal into a visible change in the water stream. Just remarkable sensitivity.
From water telephones to wireless receivers, the simple water stream is full of surprises. Okay, let's finally turn to the most obvious feature of a soap bubble. The colors. Why are they colored? It's not like the soap solution itself is rainbow colored.
No, definitely not. The colors are purely an optical effect, not pigment. And it brings us into, well, a pretty deep area of physics. The interference of light.
Interference, okay. Light behaving as waves.
Exactly. Remember, light travels incredibly fast, about 186,680 miles per second in air, a bit slower in water, and different colors correspond to different wavelengths. Red light has a longer wavelength, violet light has a shorter wavelength.
Got it. So how does a thin soap film interfere with these waves to create color?
It's all about reflections. When light hits the soap film, some of it reflects off the outer surface. That's the first reflection.
Okay, like off a window pane?
Right. But some of the light goes into the thin film, travels through the soapy water, hits the inner surface, and reflects off that. Then it travels back out through the film into the air. That's the second reflection.
So we have two reflected waves coming back towards our eye. One from the front surface, one from the back.
Precisely. And the crucial thing is that the second wave, the one that went through the film and back, has traveled a slightly longer path than the first wave.
Ah, the path difference depends on the film's thickness.
Exactly, and also the angle you're looking at it, but mainly the thickness. Now, if that extra distance traveled by the second wave is just right, say, it makes the crests of the second wave line up perfectly with the crests of the first wave.
They add together, they're in phase.
They're in phase, they reinforce each other. This is called constructive interference, and for that particular wavelength or color, the light becomes much brighter. You see a vivid color.
Okay, so if the thickness is right for red light waves to reinforce, we see red.
You see red. But what if the extra distance is exactly half a wavelength off? So the crest of one wave meets the trough of the other.
They cancel each other out. Out of phase.
Perfectly out of phase. They cancel out. That's destructive interference. For that particular wavelength, you see, nothing. Or darkness. Boyd's called it the silence of light.
Light silencing itself. I love that.
It's a great description.
And since a real soap bubble isn't perfectly uniform, it's draining, getting thinner at the top.
Right. Gravity is constantly pulling the water downwards, so the top of the bubble is usually the thinnest part, and it gets progressively thicker towards the bottom.
So thickness is changing continuously.
Yeah.
Which means the colors must change too.
Exactly. As the film thins, the path difference changes, and different wavelengths experience constructive interference. You see that characteristic sequence of colors swirling and moving down the bubble, often called Newton's rings or Newton's colors.
So the colors are literally mapping the thickness of the film in real time.
It's like a topographical map of thickness, painted in light. You can actually estimate the thickness by the color. For example, the bright greenish-yellow color corresponds to a thickness of about 50 millionths of an inch.
50 millionths.
Yeah.
That's incredibly thin.
It is. And the blues and violets, which have shorter wavelengths, appear when the film is even thinner, maybe around 18 to 20 millionths of an inch.
And what about right at the very top, just before it pops? Sometimes you see a spot that looks black or just transparent.
Ah, the famous black spot. That's the ultimate thinness.
Thinner than the violet.
Much thinner. The film becomes so incredibly thin, there we're talking around 2 millionths of an inch, that something interesting happens with the reflections. There's a phase shift that occurs on reflection from the front surface, but not the back. The end result is that for this vanishingly thin film, the light waves reflected from the front and back surfaces are almost perfectly out of phase for all visible wavelengths.
The total destructive interference for all colors.
Pretty much, yes. They cancel each other out almost completely. Very little light gets reflected back to your eye, so the spot looks black or transparent against a brighter background.
2 millionths of an inch. It's hard to even conceive of that.
It's only about 5 nanometers, just a handful of molecules thick. It's the absolute limit before the film ruptures. The black spot is the sign that the bubble is about to die.
Amazing. The colors tell us so much. Okay, one last area. Geometry again, but with multiple bubbles. When bubbles clump together, they don't just form a random pile, do they?
No, never random. They follow very strict geometric rules, again, driven by that fundamental principle of minimizing the total surface area of all the films involved. It's all about energy minimization.
There's Plateau's laws, right?
Yes, Plateau studied these configurations extensively. He found simple, universal rules.
What's the main one when films meet?
The most fundamental rule is about the angles. Wherever 3 soap films meet to form an edge or a boundary.
Like where 3 bubbles push together?
Exactly. Those 3 films will always meet at angles of exactly 120 to each other.
Always 120 degrees. Why?
Because that's the only angle that perfectly balances the surface tension forces pulling from the 3 films at that junction. If the angles were different, there would be a net force pulling the junction one way or another until it reached that stable 120-degree configuration. It guarantees equilibrium and helps minimize the overall area.
So every single three-way junction in a mass of foam has that precise 120-degree geometry.
Every single one. It's universal.
Okay, what about in 3 dimensions, where the edges meet? Can 4 films meet at a point?
Yes, and that also follows a strict rule. When 4 of those 120-degree edges come together at a single point in the center of a foam structure.
Like in the very middle of 4 bubbles squashed together.
Right. Those 4 edges don't meet at 90 degrees like the corner of a cube. They meet at the tetrahedral angle, which is approximately 109 degrees, 28 minutes.
Yeah.
Again, it's the unique configuration that perfectly balances the tension forces pulling along those 4 edges meeting at the central point, ensuring stability and minimum surface area for the complex 3D structure.
So from the simple sphere to these complex foams, it's all governed by surface tension relentlessly seeking the minimum possible area.
That's the unifying principle. Simple force, complex, and beautiful geometry.
This has been absolutely fascinating. We've gone from a simple child's toy to planetary physics, fluid dynamics, optics, advanced geometry, all hidden inside the soap bubble.
Yeah.
Let's try and recap the big takeaways for everyone listening.
I think the first thing is just appreciating that core force. Surface tension. That elastic skin isn't just an analogy, it's a real measurable force. We talked about the $2 frac 1 grains per inch for a soap film, and it dictates so much.
Right, it dictates the sphere being the primary shape because of minimum area. And we saw how Plateau cleverly removed gravity to prove that with his oil drop experiment, which then even modeled spinning planets.
Exactly. And then the geometry gets more complex but still follows rules, like the $120 interjunctions where films meet and the unstable cylinders and the beautiful catenoid shape, all minimizing energy.
And the bubble, or even just a water jet, acts like an incredibly sensitive detector. We saw how Rayleigh used vibrations to control droplet formation, leading to inkjet printing, and how electricity can either shatter a stream or hold it together.
Yeah, the sensitivity is key. From the water telephone concept to detecting wireless sparks, it shows how responsive these liquid surfaces are. And don't forget the public health angle using oil to break the surface tension and control mosquito larvae. That's physics saving lives.
Definitely. And finally, the colors. Not pigment, but pure wave interference. A direct visual readout of the film's thickness.
And measuring thicknesses down to that incredible black spot at 2/millionths of an inch. It turns the bubble into this exquisite optical instrument, proving things we could never see directly. These old experiments, they just pack such a punch.
They really do. Simple setups revealing profound truths. So thinking about all this, the forces, the sensitivity, the optics, what's a final thought you'd leave us with? Something to chew on.
Well, we just spent a lot of time talking about how the color of the film is a direct, real-time measurement of its thickness, right down to the nanoscale. 2/millionths of an inch, shown by a change in reflected light.
Yeah, an incredibly precise optical measurement tool built into the bubble itself.
Okay, so think about that sensitivity. The bubble isn't just showing us its own thickness, it's responding to its environment. We know tiny traces of impurities change the tension, which affects the thickness and drainage, changing the color patterns. Heat does it too. Electrical fields do it.
Right, it's a sensor.
It's a naturally perfect, incredibly sensitive sensor. So here's the thought. We've mastered measuring thickness with light interference in labs using interferometers. But could we harness the principle of these ultra-thin films, maybe not soap and water, but other specialized fluids or even condensed gases, to create large area, passive sensors? Imagine a surface that changes color visibly in response to minute traces of a specific pollutant in the air, or a dangerous chemical agent, or even subtle shifts in pressure or temperature, just because those things alter the film's thickness by a few millionths of an inch.
Using color change as the direct readout for invisible threats or conditions.
Exactly. Could the fundamental physics of the soap bubble, its ability to translate microscopic changes into visible optical signals, point the way to new kinds of environmental monitoring or diagnostic tools that are incredibly sensitive precisely because they rely on phenomena occurring at the scale of millionths of an inch?
That's a fantastic question. Taking the bubble secrets and applying them anew. Thank you. This has been a truly illuminating deep dive.
My pleasure. It's always amazing what you can find in a simple soap bubble.